Dear students, my name is Vivek Prasad, so working as assistant professor in textile technology department of MLB Textile Engineering College, which is located in Bhilwara, Rajasthan. The video lecture is related to the subject multifiber spinning. The topic of this video lecture is blended yarn properties involving engineering principles. This is part 2 of the video lecture. Part 1. In part 1, I have discussed about the importance of the properties of the individual fibers, which affects the properties of the ultimately blended yarn. So in general, what is our tendency? That we tend to think that if we add a stronger fiber with a weaker fiber, then the final yarn will have higher strength than a yarn which is supposed to be produced with a weaker fiber. In both the cases, the count will be same. So if we produce two yarns, one having fiber A and fiber B, fiber A is suppose cotton, fiber B is suppose polyester, and we blend cotton and polyester, and we tend to think that whatever be the blend ratio, whether it be 20-80, 30-40, any ratio of polyester and cotton, the blended yarn will have higher density than 100% cotton yarn. But that might not be the case in all the blends. This depends on in the previous video lecture I have discussed that it depends on the stress strain behavior of the individual fibers of the blend. So the entire concept here is taken from the reference the reference is an research article published in Textile Institute of Journal of Textile Institute, written by Walter J. Hamburger. Now continuing with the previous stress strain diagram, this is the diagram which I have shown in previous slide, fiber A and fiber B. Now suppose we make a yarn out of these two fibers A and B. Okay. Blending of two hypothetical fibers of the following properties is to be undertaken. This is the property of fiber A, this is the property of fiber B. Ultimate tenacity 5 gram per denier, this is 5, and ultimate elongation or extensibility 3%, and here it is 9 and 6. This is 9 and 6, fiber B. Assume a yarn comprised of fiber A and B to be D denier in size, and A is the percentage of material A and by weight, and B is the percentage of material B by weight. It means the fiber A is having a percentage of A in the yarn whose count is D denier. The yarn count is D denier, and the fiber A percentage of the percentage of fiber A, capital A, is small a, and the percentage of fiber capital B is small b. Then denier of fiber A, ठीक है, क्या होगा? Denier of fiber A is equal to, since it is a percentage having, it is having a small percentage A, small a, so its denier will be A into D by 100. Similarly, the denier of fiber B will be B into D by 100. This is the denier of the assembly of fibers. So dA, this is the denier of the assembly of A fiber, this is the denier of assembly of B fiber of the blend. Means we are dividing the whole denier into two deniers. If we add, it will be D denier, where dA is the total denier, D is the total denier of A, and dB is the material B. Now we need to investigate the first and second rupture points. Maximum strength of the composition must be investigated at these points, means these points, first rupture point and second rupture point. So we need to study the material, study the behavior of the tensile behavior of the composite yarn at first rupture point and second rupture point, because these two fibers are blended with each other. When the yarn is extended, here it is extended, so the fiber, this is the first rupture point. At the first rupture point, fiber A will break, and at the second rupture point, fiber B will break in the yarn. Now at the first rupture point, this is the first rupture point. So in a blended yarn, when the yarn is extended to a elongation percentage 3, the fiber A will rupture, but what will happen to the fiber B? It will also extend to 3%, but it will bear a load of 2 gram per denier in the blend yarn. So at the rupture point, the total load supported by the composite yarn is, suppose this load supported at the first rupture point, this is the first rupture point, it means 3% elongation. The total load supported by the composite yarn is, suppose, let us assume it is P1 equal to PA1. We are considering the load supported by A fiber, that is PA1 and PB1. But PA1 equal to, this is the load, and load equal to denier into load equal to this, load equal to denier into stress. Since stress equal to load by denier, since stress equal to load by denier, therefore load equal to stress into denier. So we are calculating the load here. Load at the supported by the composite, this is the supported by the composite yarn at rupture point 1, and this is supported by the fiber A, load supported by the fiber A. So the load supported by the fiber A will be denier, it's denier AD. Remember in the last slide we have calculated the denier of the fiber A into D by 100, and this is the stress gram per denier at this rupture point, that is 5. So we are multiplying these two, and fiber B1 equal to, this is load, BB1 is the load, and this is the denier of the fiber B, and this is the stress developed at the first rupture point on fiber B. This is 2. So we are multiplying this denier of the fiber B with 2. So now we will solve this equation P1. We put the values of PA1 and PB1. So this is D by 100. We have taken the D by 100 common. 5A, this is 5A plus 2B. This is 2B coming from here. 2B. Thus it is equal to D by 100 plus 5A plus 2 into 100 minus A. Since B equal to A plus B equal to 100 and B equal to 100 minus A. So we are putting the value of B in terms of A, and we are solving it. D by 100 into 3A plus 200. This is P1. This is load supported by the composite yarn at first rupture point. This equation P1 equal to D by 100 3A plus 200. Now again we are calculating the converting this, because we cannot individually, we can add the load supported by these two fibers, but we cannot, because the load will depend on the count, the blend of the fiber. So we cannot directly add 5 and 2, because in each case, suppose we are adding 5 stress, we are adding 5 and 2, so in each case this will be 5 and 2 in every blend, but the stress supported by the composite yarn will depend on the percentage of fiber A and B. That's why what we have done, we have converted first the stress into load. So this is here we have calculated the load taken up by the fiber A and by the fiber B, then we have added upon the load, then again we are converting the load into stress. So gram per denier, or we can say tenacity or strength of the composite yarn. So it will be P1 by D. This D is the denier. This is, we are calculating at first rupture point. So this is D is the denier of the composite yarn. So the load developed at the rupture point 1 divided by the denier, that is 3A plus 200 by 100, cancelling D, it becomes 3A plus 200 by 100. Now again we are going to calculate the tenacity of the yarn or the stress on the yarn at the rupture point 2. So for the second rupture point, the total load supported by the composite yarn is, we are assuming it is as P2. Earlier we had assumed as P1. So this is P2. P2 equal to PB2. Because at this rupture point there is no role of this fiber A at this elongation, because at 3% the whole of the fiber A breaks. So up to this elongation there is no role of this fiber. So only there is a role of fiber B. So PB2. But PB2 equal to, again we are multiplying the, this is load, we are multiplying the denier into stress. So here the stress is 9 and the denier is BD by 100. So we are multiplying and we are calculating the load. So now again we will convert the load into load of the composite yarn. We are adding the load of individual fibers and then we convert the load of the composite fibers, combined load of the composite fibers into the stress of the composite yarn. So this gram per denier, again we are calculating this P2 by denier of the composite yarn. So BD by 100 into D into 9. So D will cancel this D, so it becomes 9B by 100. Now to obtain a composite yarn, the strength of which is not less than that of a yarn comprised entirely of a weaker fiber, its tenacity in gram per denier must be equal to or greater than 5. Now what this statement says, that if we are making a yarn with fiber A, then definitely its tenacity will be 5, but we are adding a stronger fiber, so the tenacity in gram per denier must be equal to or greater than 5. Otherwise why should we add the fiber B to fiber A? Okay, so our condition should be that the blended yarn should have higher tenacity than 5, so must be equal to or greater than 5. So this rupture point should be higher than 5, because second rupture point, these two fibers I have already broken, means the yarn is broken. So at this rupture point 9B by 100, this rupture point or the stress or the tenacity is denoted by 9B by 100. So 9B by 100 should be greater than equal to 5 and B equal to 500 by 9 equal to greater than equal to 55.5%. Okay, of material B, means from this equation the value of B is coming 55.5%. Thus the percentage of fiber B in the case must be at least 55.5% of the total fiber content of the yarn to obtain a composite strength not less than that of a yarn comprised entirely of weaker fiber. So it means that in order to produce a yarn whose tenacity is higher than 5, we need to at least add this fiber B up to 55.5%. If we add a fiber B lesser than this percentage, 55.5%, the ultimate tenacity or of the composite yarn or the blended yarn will be lower than this value. What it is telling, this equation is telling, means suppose we are adding 40% of fiber B, it will not work. It will not have a positive impact on the tenacity of yarn. It is better to produce a yarn with fiber A. If fiber B is costlier, then it is better to produce a yarn with fiber A. If we are only going to add 40% of fiber B, if we need to consider the tenacity of the yarn. So it is not that adding a strong fiber will always help in increasing the tenacity of the yarn. Now, dear students, from all the explanation and derivation of the previous slides, we are going to produce a graph like this. Okay, so this is the graph. This solid line is the graph. Here it is the blend strength or tenacity of the blended yarn, and this is the blend of fiber A and B. Means at this point there is 100% of fiber B and 0% of fiber A. At this point 100% of fiber A and 0% of fiber B. In middle, somewhat in middle, 50-50. 50 of fiber A, 50 of fiber. Here the line is drawn, it is around somewhat 50, or 50 should be here, it is lesser than 45 suppose. Okay, so 45 or 50, similar like this. So this solid line represents a line, and suppose 100% of fiber B we are using, so the stress will be around more than 8, around 9. Earlier we had checked that the tenacity of the fiber B is 9, but as we go on adding the fiber A, it is getting reduced, and again here from here it is increasing slightly. So at this point, means 40-60 blend, we are not getting any advantage of, since if we get at this point, if we draw a line here, we are getting a tenacity of around 3.75 or around 4, which is lesser than 5. When we achieve 5, when we are adding, we are using 100% of fiber A, we are not using any fiber B. So only by using fiber A we are getting 5. But as we are increasing the blend of fiber B up to 40, around 40%, there is no advantage in terms of increase in tenacity, although the fiber B is having higher tenacity, but we are not getting any advantage. So that's why the stress strain behavior, or the relationship of the stress strain of the individual fibers of the blend plays very important role in determining the tenacity of the final blended yarn. So how this graph is being produced, we will discuss in our video lecture part 2.